Sorry guys, I ran out of battery. So here we go again. So when pure metals meet up with a pure metal meets up with a pure nonmetal, we're going to see an electron transfer to form the ions. This only sets the stage for ionic bonding. Okay? In fact, if we look at the electron transfer between the metal and the nonmetal from an energy standpoint, that's not going to be the driving force that lowers the potential energy of the system. That is the reason that ionic bonding forms. It's the strong electrostatic interaction between the cation and the anion that draws them together into a 3D array to form the ionic solid that's going to be the energy releasing step that drives the formation of ionic compounds. Okay? Now, in this 3D array, one cation is not going to be paired with one specific anion. When we talk about an array, it's an expanding outward structure. One cation is going to surround itself with 6 anions. One anion is going to try to surround itself with 6 cations. Okay, and it forms this extending array. So the ionic bond is not specifically between two elements. The ionic bond extends throughout a complete solid sample. Everything is interconnected by the ionic bond. Okay? Covalent bonding. Covalent bonding is referred to as electron pair sharing. Atoms share a pair of electrons, which means that each atom's nucleus is attracted to a common pair of electrons. This is localized sharing. It is directional, and only between the two atoms involved in that particular bond. Okay? So in covalent bonding, we see the formation of molecules. Because each atom-atom interaction connects two atoms to each other. Okay? Covalent bonding happens between nonmetals and nonmetals. They share electrons because each atom is holding onto its electrons tightly. They're attracted to one another. The electrons are drawn together and they're linked together in the covalent bond. In most cases, we create separate discrete molecules where all of the covalent bonding is going on inside, and they form these units. For a covalent compound, we're going to talk about empirical formulas, molecular formulas, and structural formulas. More later, previews of coming attractions. Our last type of bonding is metallic bonding. Metallic bonding is called pooling of electrons. What happens in metallic bonding is the atoms share all of their valence electrons between all of the atoms in the solid or the liquid phase. The outer electrons in metals, especially as the metals get larger, are held onto more loosely. And so if I have a solid or liquid sample of a metal, all of the electrons run in between all of the atoms. Okay? And that's why metals are shiny. It's because those electrons running in between all of the atoms and the way they interact with light because of the fact that they're moving between the metal atoms. Okay? So we can put metals together in any kind of ratio and still get metallic bonding. So metallic bonding leads to the formation of these alloys where there is sharing of electrons. Okay? So there's bonding going on, but there are not fixed ratios that have to happen between certain metals to form the alloy. Now, I mentioned empirical and molecular formulas, so let's talk about what a formula is. A formula is a shorthand way to represent the composition of a compound or an alloy, where you list the types of atoms and the amounts of atoms in the compound or alloy. Okay? Now, let me show you kind of a generic example of some formulas. Good old water. H2O. This tells me there are 2 hydrogens combined with 1 oxygen. Or CH4. For every 1 carbon, there's 4 hydrogens. The number of each atom in a molecule, or a formula unit, okay, is going to be indicated by a subscript following the symbol of the element. We can have compounds that have more than 2 elements in them. C6H12O6. Okay, so 6 carbons to 12 hydrogens to 6 oxygens. Or CH3NH2 is a way to represent a formula. This is a specific kind of formula. But these represent formulas. Okay? And they indicate to somebody who is reading something behind you that you have a compound or an alloy. If I were to write just O2, the 2 here says that there are 2 atoms of oxygen bonded together. Or if I wrote into 2 nitrogen atoms, S8 sulfur, 8 sulfur atoms bonded together into a unit. Okay? Now, we can talk about empirical formulas and molecular formulas. Let's talk about these 2. An empirical formula is the smallest whole number ratio of atoms of each type in the compound or alloy. The molecular formula is the actual number of each type of atom in a molecule of a covalent compound. So a molecular formula only applies to a covalent compound. Empirical formulas can be used for ionic compounds, alloys, or covalent compounds. But molecular formulas will only see with covalent compounds. The next one, structural formulas, is also only seen with covalent compounds. The structural formula tells us something about the order in which the atoms are attached to each other in the molecule. Okay? So let me show you some examples. Okay? All right. Now, I'm going to use glucose. Its molecular formula is C6H12O6. Okay, its empirical formula is just the ratio of the elements. Well, notice that C6H12O6, all of those subscripts have a common factor of 6. So CH2O would be the empirical formula, the smallest whole number ratios. The structural formula is a little bit more complicated. It's CH2OH, CHOH, 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 that's 1, 2, 3, 4, CHOH, that's 5, CH2OH. It's a bit messy. When you take organic chemistry, you'll look at that more closely, okay? Now let me give you another example. Benzene. Its empirical formula is CH, 1 carbon to 1 hydrogen. Its molecular formula is C6H6. And its structural formula is actually a pictorial drawing. Because benzene is a ring structure. And that would be its structural formula. So you can see the difference between an empirical formula, a molecular formula, and a structural formula. Okay, now, on our way to develop formulas for compounds, okay, let's talk Lewis. Lewis is going to do several things for us. The first thing that Lewis does is he gives us what are called Lewis dot symbols. Okay? And we're going to look at Lewis dot symbols for the main group elements, those first 2 columns, the last 6 columns. In a Lewis dot symbol, the nucleus and core electrons are represented by the symbol of the element, and valence electrons, which hint for those main group elements is the same as the outer electrons, are represented by dots around the symbol. The dots are placed one on each side before the dots are doubled up. Okay, let me scroll down here. So, let's look at the Lewis dot symbols for the first 2 periods on the periodic table. So lithium has 1 dot, beryllium has 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. The third period is going to look just the same. Going down the family, they're all going to have the same Lewis dot pattern. Now, some things that the Lewis dot does for us is it tells us for something like our metals how many electrons they have to lose to look like their nearest noble gas neighbor. For our non-metals, it tells us how many electrons they have to gain to look like their nearest noble gas neighbor. Notice fluorine is 1 electron dot of 1 dot short of neon. Oxygen is 2 dots. Nitrogen is 3 dots. Look at poor carbon. It's 4 dots that way, 4 dots this way. So, boron. Look at boron. It's going to be in a real mess. It's got 1, 2, 3 electrons. But it's a non-metal. It doesn't like to give up electrons. It doesn't like to form ions. Okay? So the Lewis dots are going to be a quick way for us to look at just those electrons that are going to be involved in bonding. Okay? Now, the Lewis dot symbols we're going to use in conjunction with the Lewis octet rule. The Lewis octet rule states that atoms lose, gain, or share electrons to achieve 8 valence electrons, with helium, hydrogen, and lithium being exceptions because their outermost shell, when they form helium has an outermost shell of 2. Hydrogen, to look like helium, would have to gain 1 electron, would have 2. Lithium loses 1 to look like 2. So that we're dealing with that 1s subshell, which can only have 2 electrons. Okay? So atoms gain, lose, or share electrons to achieve 8 valence electrons, with helium, hydrogen, and lithium being exceptions because the first shell only has 2 subshells, which can only, the s subshell, which can only hold 2 electrons. So we're going to first start by applying the Lewis octet rule to the formation of ionic compounds. Then we'll move on to covalent compounds, and then lastly we'll talk about alloys. How am I doing on time? Okay. Now, we already know that nonmetals want to gain electrons and metals want to lose electrons. So if I bring a metal in contact with a nonmetal, we should see an electron transfer. Metals lose, nonmetals gain. So if I brought sodium in contact with chlorine, the sodium ion is going to give up one electron. If you draw its Lewis dot symbol, it's only got one dot to form the sodium plus one ion. Chlorine is going to want to pick up an electron to come to the chlorine ion. If we look at the energy of the electron transfer, it takes 496 kilojoules of energy to remove 1 mole of electrons from 1 mole of gaseous sodium ions. You get only 349 kilojoules of energy released from the chlorine when it takes in the electron. So notice it's taking more energy to remove the electron from sodium than you get released when the chlorine takes in. So the electron transfer part of this process of moving toward an ionic compound is endothermic. Think about that, guys. It's endothermic. It's energy absorbing. Okay? 147 kilojoules of energy has to be input to make that transfer happen. Okay? We're at a deficit here energy-wise. Okay? This means that the potential energy of the system is now higher than the individual atoms by themselves when I have formed the ions in the gas phase. The whole purpose behind bonding is to lower the potential energy of the system. So, bonding happens to lower the potential energy of the system. Right now, we're upped the potential energy of the system. So there's got to be something else going on or we wouldn't have ionic compounds. The overall process of forming ionic compounds is actually very exothermic. And the energy release happens when the ionic bond forms. When I take these positively charged particles that have opposite charge and we allow them to come together to form the ionic solid. The energy involved in formation of the ionic solid is referred to as lattice energy. So it's energy associated with the formation of a crystalline lattice of alternating cations and anions. Now, when you look at a chart of lattice energies, you're going to see positive values, and that's because when lattice energies are written down, it's the amount of energy needed to break a mole of bond. The same magnitude of energy is released when a bond is formed. When we form a sodium chloride, mole of sodium chloride bonds, we get a lot of energy released. For sodium chloride, there's 786 kilojoules of energy that are going to be released when 1 mole of ionic bond is formed. If we're 176 kilojoules of energy in the whole, and we now get an influx of 876 kilojoules of energy, then we're okay. The overall process is exothermic. So, hint, 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 very, very important to remember, okay? Ionic bonding happens because of the tremendous amount of energy that can be released when the ions, once they're formed, can form the ionic bond, okay? It's not the electron transfer that is the driving force behind the formation of the ionic compound. It is the energy released when the ionic bond forms. I don't care what a middle school teacher told you. 111 kilojoules of energy released. So here's a pretty picture, okay? All these ions are far apart, but they're attracted to each other because they have opposite charges. And they start to coalesce from the gas phase. They start to close in on each other, okay? And they form the solid, which has this array. So notice that this guy, I can see 4, this is the chloride ion, I can see 4 sodium ions around it, and there's a sodium ion behind it. We're only looking at the outer edge, okay? So they've coalesced into this array of positive and negative ions. Now, the next thing for us to do is write the formulas for ionic compounds. And the empirical formula of an ionic compound, of course, is going to depend on the charge of the ions and the way the electrons would be transferred if I have the pure elements. Okay? So we're going to look at how these guys are going to come together next. And this is a good place for me to stop.